If you want to know more about RAS, we also have the robotics program at Udacity that actually focuses more on RAS, so it's not all applied to self-driving cars. And that's it. Thank you very much. So in the first 10-minute talk, I'll describe an abstraction that we designed for modeling prediction problems. And this abstraction is at the heart of the platform that we're building at Select. The platform is called PDB, and PDB is short for prediction database. The second talk will actually be about the architecture of the platform itself. So the way we think about our platform is it's a software layer. So it works like a database in the sense that you can query it. You can query it for data. If data is in the database, you get back the data. If it's not, you get back a prediction along with confidence and some provenance information. And when we were building it, we wanted it to work with all kinds of data sources. So it should work with text, it should work with numeric data, with images, geospatial data, time series, etc. And it should work with all kinds of prediction problems. So it should be able to do out-of-the-box time series predictions, classification, anomaly detection, right, so the entire list. So before we could build something like this, we found we needed the right abstraction. Right? We needed a flexible abstraction to talk about prediction problems. So the analogy here is with SQL and what it did for databases. Right? So what SQL did for databases, it decoupled the description of the data we want to fetch from where this data is stored and instructions for actually accessing the data. So this allowed us to focus on the logic, and we outsourced kind of the fetching of the data and all these mechanics to the database. And we want something very similar, right? Except we want this for data science. We want to be able to focus on the fun pieces, the modeling of the data, figuring out the right features, building the right models, and have the work of building the pipelines, maintaining them outsourced to the prediction database. So to explain the abstraction itself, I do this with a simple toy problem. So I use the popular movie recommendation problem. And the way I want to visualize the data is in sheets. So like an Excel file. And in this case, there's 4 sheets, tags and ratings. And this is similar to the movie lens dataset. So the movie has all kinds of features of the movies in our dataset. So in this case, title, genre, the year in which it was produced. Users is similar. So users has features of the user. Right? It identifies each of the user, it gives them an ID, and it does have the name, age, location, and gender. Tags and ratings are a bit different. Right? Tags and ratings are both interactions in that they involve both the movie and the user. So tag is something that any user who watches a movie can give that movie. So it can be random text. So some users put in something to do with the genre, some users tag the actors in the movie, it can be arbitrary. And finally ratings, right? And for the problem of predicting or movie recommendations, ratings is really what we want to predict. It's typically very sparse. Not all users have seen all movies. And the task here is for a movie user pair where we don't have a rating in the system to predict that rating. So what does the PDB abstraction look like for this data set? For every cell in this Excel file, we model it as a key value pair. So the value is whatever happens to be in that cell. If it's an image or text, it's a vectorized form of it. And the key is how we address that value. Right. And in this case, the key is uniform. It always consists of 2 components. So the first component is an operation. Operation tells us kind of what kind of data it is. Right. So it's what kind of relationship are we trying to model. The second component is a pair of IDs. So ID1 and ID2. And in general, they talk about the entities in our data set. So in this simple case, there are 2 kinds of entities. There's the users and there's the movies. So the users here are from 1 to n, the movies from 1 to n. And you can think of these as points in a graph. Right. So these are vertices in a graph. And every data point we have in our data set will be an edge in our graph. So for instance, take rating. Right. So this is one data point. It says that the rating that user 1 gave movie n is a 5. Right. So the operation here is rating. It tells us what kind of data 5 is. ID1 identifies a particular user, and ID2 identifies a particular movie. Right. So now the movie sheet. Movie sheet looks like this. Now we no longer have 2 entities involved. There's just 1 entity, the movie. The operation is either genre or title. And since we have only 1 entity, ID2 is a null, and ID1 is either movie 1 or movie n. So it's the genre of movie 1 is a comedy. And we do the same thing for users, right? So the gender of user M is male, and tags kind of looks like ratings. So operation is tag, ID1 is user 1, ID2 is movie 1, and the value is a vectorized form of Screwball comedy. So we've actually found that even though this as a representation looks very simple, it's able to model all kinds of relationships in the data. We model fairly complicated sets of relationships, and we can model all problems using the same abstraction. And in general, it looks like a tensor completion problem. In particular, it looks like a 3-order tensor completion problem. 1 dimension is operation, and you can view the data as slices along operation. And each of those slices has 2 axes, ID1 and ID2. And anytime we want a piece of data that's not in the data set, that looks like a tensor completion problem. So we specify operation, we specify ID1 and ID2. So that forms the key, and we query for the value. So what do we get with an abstraction like this? So what we found when we were building pipelines is inevitably we had to stitch together several data sources in order to get something good out of the system. Different data sources organize data differently. They call the same thing different names. So typically it's hard to stitch them together. It requires some custom work each time. But once we process them and had them represented using some common vocabulary, stitching them together is much easier. And when we have intermediate models, intermediate predictions, they're easy to use across multiple pipelines, across multiple predictions. The other thing we found was what would normally happen is we would start working on a data set, we would build some models, be able to predict something. And immediately someone would want to predict something else. And when we had stored our data and our models in kind of very specific forms, so when we had feature vectors, for instance, it wasn't trivial. So predicting something else meant building one more pipeline to do that. Here we have an abstraction that's not tied to what we are predicting, and asking a different prediction question is really easy. And the last thing is, so now we have this abstraction. All our algorithms are coded only to work with this abstraction. We have nothing else that we deal with. But that means we know exactly how to lay out data for efficiency, both for compute and for querying. And we don't have to redo this work of optimizing, how should I partition my data, what indices I build, every time we get a new data set. And all our pipelines look homogeneous. They are built based on exactly the same abstraction, it's the same code, making maintaining them really easy. So what we found was having an abstraction like this that let us decouple what the data was and what ETL pipelines were from what the algorithm and machine learning pipelines was really helped us build our platform really efficiently. So after the break, I'll talk in a bit more detail about what our platform architecture looks like. Thank you. My name is Siddharth. A little bit about me. I've worked in the Valley for many years, at many of the companies listed above. I currently work at GitHub. I joined about 10 months ago to work on various data infrastructure challenges. I'm also a co-chair for many of the KubeCon conferences. One of them is this one. I'm also a maintainer on Apache Airflow, and in my spare time, I spend time with my family. One of which is like a 1-year-old girl, and the other is like a 5-year-old boy, but they both act the exact same age. So Apache Airflow, first of all, a show of hands. How many people have used it? Okay, how many people have heard of it? Okay, more. Okay, good. So what is it? In a nutshell, it's a platform to programmatically author, schedule, and monitor workflows. Workflows are things that do things. They're also known as DAGs or directed acyclic graphs. And the first way most people come to know Airflow is through its UI. That's essentially the first interaction most people have, so I thought, why not just walk you through the UI a little bit. This is the landing page for the Airflow web server. When you hit it, if you have Airflow running at your company, for example, there are multiple columns here. The first column, let's ignore this one. The first column is just the name of the DAG. And then next to it is a toggle switch, which basically tells you whether the DAG is enabled or disabled. So if you're doing some sort of maintenance on some system, and let's say you're doing ETL, some sort of ETL that's reading data from, let's say, MySQL and writing it into Redshift, and let's say you're doing some maintenance on MySQL, you might want to disable that DAG. The next column over is sort of a schedule, and it supports multiple types of schedules. So it supports like cron scheduling. You can also specify, like, because this is written in Python, which I'll talk about a bit more. It supports like Python date-time semantics, and it also has some built-in enums, like hourly, daily, monthly. The next column, of course, the owner, and then this sort of a slightly older UI, but the stuff in trunk is much, got a few more columns here, but this basically tells you that this had 3 tasks, and all of them completed successfully in the last run of that DAG. This one just started, and there's 1 task in progress, it's light green. And then down here, this says that this DAG had a few tasks that successfully completed, but then it hit an issue, and then that's all the reds that are failed tasks. And then within that DAG, within this directed acyclic graph, the bottom of, like, the downstream of that, those will never run. Those 2 orange globes just tell you that the bottom part of the DAG never actually executed because upstream of it, some tasks failed. And finally, there's some sort of quick links to hop around the UI. Let's say you pick one of these DAGs and you click in on it. You'll come to this view, which is the pictorial view of your graph that you're executing. This is a graph of computation. And so these are the tasks, after task, after task, after task. So these tasks are chained together in a dependency tree. So this is the first one to run, after which, if it's successful, this will run. If that's successful, it'll go down these 2 paths. So how many of you have used something else, like a DAG scheduler of any sort, just to get a sense? A few of you? Okay, cool. Not too many of you. So this is sort of the pictorial view, and then another view is the code view. So this DAG is actually represented in simple Python code. What differentiates this, like Airflow, from, let's say, Uzi or Azkaban, which are also workflow schedulers, is that you have to deal with like XML definitions, or in the case of Azkaban, you actually have to zip a directory of files, and that directory actually mimics the layout of your DAG. And it's very cumbersome if you start trying to make structural changes to your DAG to CD to multiple directories to change config and stuff. Airflow says that your DAG is just going to be code, and as a software engineer, you apply all the best practices of software engineering to this code, so you get all the benefits of like good software hygiene, but just being a good software engineer. You don't have to manage another like DSL or like, you know, XML or something. So this is exactly what the code looks like. Let's say that you've run your DAG multiple times now, and you want to see historically how it's done. So this is called a tree view, and the tree view basically shows you a few things. So this is your DAG represented as a tree. Okay. The round circles at the top are the status of a DAG run. So let's say your DAG were to run every day. Over 30 days, you have 30 green circles if they were all successful. And this light green one just tells you that that's the one in progress. And then all the squares are actually task statuses. So whereas the round circle up here, the DAG status, these are all task statuses. And they can either be, as you can see, think, which means that they were skipped because they didn't need a condition. So they were just conditional tasks that only run maybe every 3 a.m. every day. In addition to what your DAG normally does, it also takes a backup. So that's why you would end up skipping a lot, like 23 other hours a day. And then this is the current DAG that is being run on this edge, and you can sort of see this green one is the one in progress, and downstream of it are 2 that we need to run afterwards. So this is sort of a tree view of your DAG, and you can see like over a course of days, I think this is 25 hours, these are hourly DAGs, it's got 25 runs. How about looking at the actual performance of your DAG? So you can look at a specific DAG run, and you get a gap view, and the gap view shows you that, okay, for this specific DAG, it spent 5 minutes waiting for some data to land, it says waiting for telemetry ingest. Then it spent about 10 minutes doing a Spark job to aggregate that data Spark job, and then it had to import that data into a database, and that's called wait for replicator, but essentially it spent 2 minutes. So the most expensive part of the DAG seems to be the Spark job, which makes a ton of sense. This is some sort of aggregating job. Now, how is it performing over time? So this will give you the time view. So whereas in this case, each task in the DAG, where an item here, these are the tasks in a specific DAG, we're taking each of those and making them a series. So they're now, this is the aggregate data Spark time series, and these are all the other ones. And these are all fast, so they take almost no time. This x-axis is the runtime of the DAG, like when was it scheduled to run. If it's running every hour, so every hour of the day, there'll be a dot here. The y-axis is the duration of that task. So this DAG is running over multiple months, in fact, but this is how long it takes in terms of fractions of an hour. So what we found out was in January of this year, our Spark jobs are just getting slower and slower and slower and slower, and of course these are the weekends, so things are kind of better, but it's just getting slower and slower and slower. And if we didn't have this sort of monitoring view built into Airflow, we wouldn't have noticed this. Our data scientists optimized the Spark job, and then they brought the performance back down to 0.3 hours, 18 minutes or something, instead of like over 30 minutes. And then they did another optimization back here to bring down time, and of course they added more like features and things got worse. automate things like ETL pipelines, machine learning pipelines, also just simple cron jobs that run on one machine, especially if you're running in the cloud and that instance can go away. You sort of need some reliable cron that's distributed, that's going to run even if a machine crashes or something. And what should a workflow scheduler do for you? Right? What are the table stakes? So the table stakes are, first of all, it should schedule a graph of dependencies. So if upstream dependencies succeed, then downstream can run. It should retry if things intermittently fail. So it should handle the past failures by retrying. It should report and alert on any type of failure. So there should be something that comes bundled with it, but in all of our companies, we all use a different hodgepodge of like monitoring and alerting. So it should easily integrate with those. It should give you a built-in performance over time if you sort of stop. It should enforce some sort of SLA alerting, because if you're the person in charge of workflows, you probably care about correctness and timeliness, right? If an hourly job is taking 3 hours to run, you're probably going to get paged. Okay, so we're quickly running out of time. So what does Airflow add on top of this? It adds the fact that it's configuration as code, it's usability in terms of a stunning UI, it's got centralized configuration, resource pooling, and it's very easy to extend because it's essentially Python code base. All right, so I'm going to really run through this just to give you a sense of this. So this is an actual use case that is powered by the Airflow DAG you saw. In the previous company I worked at, we were collecting email metadata live from customers being other enterprises, and that data would land in S3, in an S3 bucket, and every hour a Spark job would run to aggregate like some statistics on that message data. And then we would post the aggregates back into a different S3 location, and that would cause notifications to be sent over SNS and SQS. And then we would launch a fleet of importer nodes running in what's called an autoscaling group to read all of this data and transfer it into a database in a structured format, where a UI could be used by like some sort of NOC person, network operations center person, to actually analyze the results of all the emails that they got. All of this was being done by Airflow orchestration and was handled by the same DAG that we just looked at. So this is sort of the stuff you can do. We do a lot more than this, like model building, model deployment. Everything can be done through Airflow primitives. It's been around for about 2.5 years. So it was created in Airbnb in 2015, and then Max launched it in Hadoop Summit that same year. And then in 2016, we got it into the incubator, and today it has 2,400 plus forks, 7,600 stars, 430 contributors, 150 companies officially using it, and we are at like 14 committers and maintainers right now, and we're always growing. So that was about it. Thank you. If you have questions, you can come up.
I appreciate that someone recognized the origin of this name. Had to spend a lot of time explaining it to people who are not from the US why this was the perfect name for feature engineering. So yes, I'm Leah McGuire. I'm a principal member of technical staff at Salesforce, working on Salesforce Einstein. I've mostly worked on our AutoML initiatives.
And my name is Mike Powell. I also work with the Salesforce Einstein platform. I manage our automated machine learning product initiative. And today, just like Leah said, we're going to talk about our magical feature engineering process called transport implementation. So before we get started, you all know that Salesforce is a publicly traded company. We have a very active legal team. So this is a forward-looking statement. Long story short, don't buy Salesforce stocks, just based on the session, all right? With that out of the way, let's get started.
Right. So let's presume for a moment that your data store is represented by this closet. If that's the case, then I'm going to say, lucky you. Your data store looks really nice. Things are where they're supposed to be. You have some indication of what they're supposed to do based on their location, and everything appears to be filled out. But like your actual data store, this closet, your actual data store basically looks nothing like what you want to feed into a machine learning model. So machine learning models generally expect some sort of numeric input into the algorithm that's actually going to make the prediction. And in order to get from something like this closet or your data store, you're going to have to do a lot of steps. And it's surprisingly few steps different to go from something like a closet than it is to go from something like a data store. So raw logs require a lot of work in order to create actual features from them. And this is made worse by the fact that most people's data stores don't look like that. They look like this, right? So you may not know where to find things. Things are not necessarily in the place. They're not filled out. You have to do some detective work in order to figure out what the right use for different pieces of information are. And so as you can imagine, this is a very labor-intensive process. This is actually, I would say, where most of the work in feature engineering or in machine learning ends up happening is in the feature engineering.
So to make things slightly harder, so Salesforce is an enterprise company, so we are a B2B company. Our customers are other businesses, so each of them brings their own messy unclean closet. And so we have to spend a lot of time to do feature engineering, ETL, and processing of the data. Another important thing that I want to mention, which most people don't understand in the enterprise space, is since each of these businesses have their own data, we cannot commingle the data because it's a trust issue, it's a privacy issue. Imagine using Google data for Uber and vice versa. There will be a lot of problems there. So we have to figure out that how can we, based upon the type of the data and the shape of the data, what kind of feature engineering process that we can do. Also, because we have hundreds of such customers in business, like sitting and hand tuning and doing feature engineering for the individual closets of data, that's just does not scale. So we have to sort through different methods. And today, machine learning algorithms take the center stage in AI. Like every company has been spending a lot of time in improving their algorithms. I always see that there's a research or some research paper, but they're trying to get a fraction of a percentage above some other algorithm as it comes to accuracy. However, what we see in the real world, especially in the enterprise space, the bottleneck is not really in the modeling algorithms. The bottleneck is actually feeding the data into those algorithms. So we have invested a lot of time in doing our own feature engineering process. So we will talk more about that.
Right. So if you think about what a machine learning algorithm wants, it wants something like this. You've got a nice, clean numeric input that you use to predict some particular label. So in this case, it's a categorical label. And the question is, of course, how do you get from some data that may be unrelated into this numeric output? And the answer is that it really depends on the particular data that you're inputting, right? So you have to customize how you do feature engineering for the data that you see. And this is what most of the data scientists' time is spent on. And the way they do this is they look at sort of the shape of the data, the distribution, the size of the data, how much of that data is filled in. Color is a little bit of a stretch, but you get the general idea. Like you're really digging deep into what that data is. So you can think of color as something like the type of the data, right?
And so this metadata-driven feature engineering is very common what we do in Salesforce. So here's a snapshot. Like based on the type of the feature, we're doing different kind of feature engineering processes automatically. For instance, if the feature is numeric, we would do imputation, we would track null values, we would scale and do log normalization based upon the type of the numeric feature that is. We would do smart binning. Smart binning is interesting because these are numeric features. We are not just bucketizing the features manually, but based upon the information gained with respect to the label, we would automatically figure out buckets. When it comes to categorical features, we would do similar transformations. In addition, we would do one-hot encoding. If there's a lot of different categorical values available, we would do dynamic top-tier pivot. When it comes to text features, hashing is very common. We would do TF-IDF and word embeddings. We would also do sentiment analysis on some of this text, and language detection is also very important because some of this text based on the language, how you're doing feature engineering really depends. The next one is temporal. This is a time-based feature, which is actually very important. So we do things like time difference. If your time feature has seasonality in it, so seasonal importance, we would do circular statistics to actually capture those signals. Also, closeness to major events is another custom feature engineering that we do in order to capture seasonality.